Before we dive in, remember to check out Part 1 for the basics of turbochargers. In this video, we'll explore how turbochargers work, their performance benefits, and the advanced technology behind them. At its core, a turbocharger has two main sections connected by a single shaft. On one side, you have the turbine, which lives in the hot side of the system. On the other, the compressor, which operates on the cold side. This entire rotating assembly, the heart of the turbo, is known as the CHRA, or Center Housing Rotating Assembly. Instead of wasting the energy from your engine's hot exhaust, a turbo puts it to work. These gases are channeled into the turbine housing, spinning the turbine wheel at incredible speeds, sometimes over 200,000 revolutions per minute. That's more than 30 times faster than your engine's redline, harnessing energy that would otherwise be lost out the tailpipe. This rotation is transferred via the shaft to the compressor wheel. It acts like a centrifugal pump for air, pulling in fresh atmosphere, compressing it, and creating positive pressure, or boost. This pressurized air is then forced directly toward your engine's intake. But there's a consequence of compressing air. It gets very hot. This is a problem because hot air is less dense, meaning it carries less oxygen. Worse, it dramatically increases the risk of engine knock, a destructive phenomenon that can quickly damage internal components like pistons. That's why the intercooler is an essential part of the system. Acting like a radiator for your intake air, it cools the hot compressed charge before it reaches the engine. This cooling effect makes the air dense again, packing it with oxygen. The result is you can safely add more fuel, unlocking a more powerful, efficient, and reliable combustion process. Let's start with a common 1.6-liter naturally aspirated engine. It relies solely on atmospheric pressure to fill its cylinders with air, a process that's fundamentally limited. That's why it might produce around 120 horsepower, a respectable figure, but it's at its unassisted potential. Now, add a turbocharger. It uses exhaust gases to spin a compressor, actively forcing dense pressurized air into those same cylinders. This is called forced induction. With a denser air charge, the engine can burn more fuel, and suddenly that same block can push 180 to 200 horsepower. That's a huge performance jump, a concept known as improving power density. You get the power of a much larger engine without the added size or weight. This is why you see small turbo engines in everything from hot hatches to family SUVs. They offer big power on demand. Of course, it's not perfect. There's often a brief delay before the turbo delivers full power, known as turbo lag. This happens because the turbine has mass and needs time to spin up. Modern engineering has greatly minimized this, but the fundamental principle remains. That's why systems like twin turbos were developed. In a sequential setup, a small turbo provides instant low-end response before a larger one delivers top-end power. Parallel systems use two smaller turbos that spool up much faster than a single large one, sharpening throttle response. Then you have variable geometry turbos, or VGTs. These are truly ingenious, using adjustable vanes to alter exhaust gas velocity. At low speeds, the vanes narrow, spinning the turbine faster to reduce lag. As revs climb, they open up for maximum flow. Another smart solution is the twin scroll turbo, which separates exhaust pulses to improve turbine efficiency. The bottom line, a turbo doesn't just add power, it allows modern engines to balance performance and fuel economy. This enables downsizing, where a smaller engine is frugal on fuel, but delivers big power when you need it. That's why today, you'll see small 1.0 or 1.2-liter engines making power that used to require 2 liters or more. It's the engineering that makes modern cars both efficient and thrilling to drive. Don't forget to like, share, subscribe, and stay tuned for Part 3.